Welcome. In this session, we're going to explore the gradient one form and the Jacobian matrix. Let's now take the work from the previous sessions that we have and put it together. So we define, and let's be specific. This is the gradient one form. And let's underline what we're defining, the gradient one form. We'll write this as, this is the gradient, and we'll say it's a one form, so our way of doing this is we're going to underscore this. Most authors don't. We will. So the gradient one form of a function is defined for us as this one form that we've written a number of times, which is the partial derivative of the function with respect to the first entry, the partial derivative with respect to the second entry, and so on until we've represented the partial derivative of the last entry of the underlying vector. So now we can write the derivative in direction v of a function at a vector argument to be, we take the gradient one form evaluated at that vector argument w, and we multiply that one form by the vector v. Now, observe carefully that this definition is not what we see in most optimization texts or calculus texts. Most will represent the gradient as a vector. Some authors will be kind and will put a little arrow on top of the gradient. Most will not. They'll simply have the gradient. And what we'll do is we'll use the one form, and I'll try to remember to say one form, but if you catch me saying just gradient, just saying the gradient of a function, don't worry. What you can do is just constantly recall that this is a one form. Now, that lets us really concisely write the directional derivative of a function in a direction v. Another term that we'll sometimes have, we won't come across this very often in our course, is we might be given a function that maps a real number into a vector space, and we'll use m as the number of entries. And this might be written as a vector function of a scalar argument. And the way that we'll handle that is we will say that the derivative of this is the entry-wise vector, derivative of the function. So we will say that the derivative of the function with respect to its scalar argument evaluated at some scalar argument, evaluated at some scalar argument, we will define that as, we'll say this is f1 prime at that value, f2 prime at that argument, and so on until we've represented number m prime at that argument. And as I said, our use for this will be very occasional. What we'll come across more often is a combination of these. That is, we'll come across a function that has a vector argument and produces a vector value. This arises in particular in neural networks. So if we're given a function that takes an n-dimensional vector in and produces an m-dimensional vector out, and we might write that as a vector function of a vector argument. We'll handle this in two ways. We'll basically take this material and we'll combine the material over here into one thing. So that we'll begin by we'll write the function this way. We'll say that this is function 1 that has a vector argument, function 2 that has a vector argument, and so on until we get to function, this will be an m that has a vector argument. And when we have this concept, what we can do is we can say, well, here what we did was we differentiated each one of these functions separately. Why did we do that, by the way? Well, the reason is that function 1 and function 2 could be utterly different. They're in general, that's the whole point, is that function 1 and function 2 are different, and for some reason we're gathering them into a vector. If function 1 and function 2 are different functions, then it's appropriate to represent their derivatives separately. Likewise, here, if function 1 and function 2, now this function 1 is taking a vector argument and mapping it to a scalar. Here function 2 is taking a vector and in general mapping it to a different scalar. Well, what we can do is we can take the derivative of function 1 quite similarly, right? And the way we do that is we would take the gradient 1 form of function 1. And let's define that as, now we have to be careful in our notation. So this will have n entries. So there will be this derivative of function 1 with respect to variable 1, the derivative of function 1 with respect to variable 2, and so on until we get the derivative of function 1 with respect to variable n, because there are n in the domain of that function. We can define the gradient of 2 as, that will be the derivative of function 2 with respect to variable 1. The derivative of function 2 with respect to variable 2, and so on until we get the derivative of function 2 with respect to variable n. Now, one of our rules in linear algebra is see a bunch of numbers, gather them into a vector, see a bunch of vectors, gather them into a matrix. Well, now what we have are rows, and we'll apply a new but very similar rule, and that is see a bunch of rows and gather them into a matrix. So what we can do is we can write a matrix that looks like this. This has gradient 1 form of function 1, gradient 1 form of function 2, and so on until we get to gradient 1 form of function m. And there are m because that's how many we're outputting. This has a special name, and we will define this as being the Jacobian matrix of the function. So this is the Jacobian matrix, or we'll often say just the Jacobian. So as I mentioned, sometimes I will say just the gradient, where you'll have to understand I mean the gradient 1 form. Sometimes I'll say just the Jacobian, where you'll have to understand that what I mean is the Jacobian matrix. Another way the Jacobian matrix is defined is as entries. Some will say that entry ij of this matrix is the partial derivative of function number I, so that's the row, with respect to variable number j, and that's the column.